Hello everyone and welcome to the week 8 session 3 of NPTEL course in pharmacognosy and phytochemistry. In the previous two sessions, we saw a set of very beautiful pigments that are present in plant. We call them as carotenoids, and those were tetraterpene derivatives, that is C40 derivatives. In this session today, we will be studying quinone and quinone containing drugs. So what are these quinones and quinone containing drugs? Quinones are compounds which are widely distributed in nature. They are a ketone dione moieties that are abundantly present in plants belonging to the family such as your Polygonaceae, Rubiaceae, Leguminosae, Rhamnaceae as well as Liliaceae. If you recollect, in the previous sessions when we studied glycosides, we have studied compounds such as senosides, aloin, all those are anthraquinone derivatives. Senosides belong to the family Leguminosae, whereas if you go to see your aloin, that belongs to the aloe vera plant belonging to the family Liliaceae. Now apart from the plants, they are also found in lower plants like lichens or fungi. They possess numerous biological activities, and the most striking one being purgative, that is their ability to irritate the GI mucosa. So if you remember your barbaloin or aloin as well as if you remember your senosides, those were the anthraquinone derivatives which had a strong purgative action. But apart from that, your quinones also possess a very strong antibacterial, anti-tumor, in some case cytotoxic, diuretic as well as hemostatic effects. So what are these different quinones and how do we see them? So quinones, depending upon the nucleus in which they occur, are divided into different classes. So if the nucleus is a benzene and you apply a quinone, quinone is a diketone derivative. So if to the benzene you apply a diketone, you get what is called as benzoquinone. To a naphthalene you apply a diketone, you get a naphthaquinone. To your anthracene, if you apply your diketone, you get your anthraquinones, and to a phenanthrene nucleus, you get what are called as phenanthroquinones. Now, these are not all. In addition to that, if you just extrapolate this to the microbial sources, you might have encountered something like an antibiotic, especially the antibiotic belonging to the tetracycline derivatives. Your tetracycline derivatives are also examples of your quinones which have a 4-ring structure rather than the previously studied, or now what we are studying, the 3-ring structure. So what role do quinone play in plants? Now quinones have a very good ability to undergo redox reactions. So they form what are called as quinone and quinols. So this might just get converted to a dihydroxy, and you can have a benzene like aromatization here. So that kind of interchange is very quick with quinones, and as a result they form a part of your redox systems which are involved in the respiratory chain. So if you see the mitochondria, there is a respiratory chain called as the electron transport chain. So quinones are the part of electron transport chain due to their ability to undergo redox reactions. Now apart from that, they play a very good role as plant pigments, and also like I said, they are defensive molecules. So they are antimicrobial, and for larger or higher animals they cause GI irritation, thus preventing animals from consuming the plants. Now going to biosynthesis. So how are they synthesized in nature? The biosynthesis of quinones occur via different pathways. Now a majority or a major pathway for biosynthesis of quinones is a polyketide pathway. So what happens in polyketide pathway is something very similar to your acetate malonate pathway. So if you recollect your acetate malonate pathway, you had your acetyl CoA. Now this acetyl CoA in presence of an additional CO2, acetyl CoA is a C2. So in presence of additional carbon dioxide and factors such as biotin, in presence of acetyl CoA carboxylase will add the CO2 to form what is called as malonyl CoA, and then subsequently it will go on adding more and more of this acetyl CoA. Now what happens is this structures then polymerize. So imagine this is a 2 unit, add one more acetyl CoA to it, you will form a 3, that is a C6 unit. So this is C4, you will get C6, C8, C10 and so on. Now imagine 8 such units joining. So you can just count 8 very easily by counting the ketones out here. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 such kind of acetyl CoA getting converted to malonyl CoA and being added up will give you what are called as polyketides. Normally when you went in your acetate malonate pathway via your fatty acid synthesis, what happened is this ketone group got converted into alcohols and thereafter they got eliminated. So eventually what we got was a hydrocarbon chain to give you fatty acids. But imagine a scenario where they don't get reduced completely. Now imagine if this reduction is partial and that leads to cyclization. So this cyclization will create what is called as a typical anthracene nucleus. Now from this anthracene nucleus, imagine you have a further oxidation. You get what are called as anthraquinone derivatives. The steps proceed further to undergo reduction. So you have mostly your plants having anthracene or anthraquinone or even hydroxyanthraquinone. So in plants this remaining ketones get converted into hydroxy derivatives and you have hydroxyanthraquinone derivatives. So in the end product what comes out is a polyketide product. This polyketide product kind of gets reduced partially to cyclize into a tricyclic system for biosynthesis of anthraquinones, and this tricyclic system further undergoes reduction to form what are called as hydroxyanthraquinones. Not only that, it might undergo oxidation to form a what are called as 9,10 anthraquinone derivatives. So biosynthesis of anthraquinones mostly happen via acetate malonate pathway, but there are few quinones which have been synthesized from the isoprenoid pathway. There are few quinone derivatives which have also been synthesized via shikimate pathway. Now if you see naphthaquinones in a very similar manner, here again you can visualize. Here you have your acetyl CoA. You can count how many acetyl CoA you are using by just counting the number of ketone moieties. So 1, 2, 3, 4, 5. Okay, and the sixth one is basically what is kind of involved in the joining reaction, and this acetyl CoA, like I said, will first undergo a preliminary cyclization. So you get an all or you get an phenol being formed. Then it will undergo a secondary cyclization. So you get 2 ring structures, but in the process a subsequent oxidation converts it into a quinone. So it's basically a very simple process wherein your polyketides first reduce, join in, cyclize to give you a cyclic structure. Thereon it undergo oxidation to add a quinone moiety, and some of this ketone moieties undergo reduction to develop hydroxy substituents on the quinones. So naturally most of the anthraquinones you will find hydroxy substituted. Now let's take a simple case, or let's study today a class of quinones which is your benzoquinone. Benzoquinone, as the name implies, It is a quinone or a diketone substitution on a benzene ring. Now you can see here, as the case be with embelin, there is a 1,4, and even in thymoquinone there is 1,4. But in nature there are also quinones which are orthoquinones. Orthoquinones means the second ketone will occur here at the ortho position. But compared to paraquinones, orthoquinones are thought to be comparatively unstable, and relatively their occurrence happens in a very less as far as the plant kingdom is concerned. So you will find majority of the benzoquinones being your paraquinones, that is your 1,4 quinones. Now once they are formed quinones, like we saw in biosynthesis, they will undergo hydroxy substitution to change their polarity. Now as compared to embelin, if you see this second compound thymoquinone, you can recollect of this structure. If you recollect this structure, you will understand that this is typically a C10 that we did previously, or that we studied previously when we did our volatile oils. So this is one example. So thymoquinone is one example of a quinone derivative which has come out from your isoprene synthesis. So you remember this? This is your 1, 2, 3, what we called it as head, 4, 5, cut it here, and then 1, 2, 3, 4, 5, cut it here. So this is a typical isoprene derivative, whereas embelin is more of a polyketide synthetic derivative. So like I said, just put an emphasis, majority of the quinones have been brought in by polyketide pathway, but there are some which are derivatized from your isoprenyl pyrophosphate, or what it called as acetate mevalonate pathway. In some cases they are also derived from the shikimate pathway. Now depending upon that, you might have different substitutions occurring. In some cases you will find long chained ones, in some cases you might have a short substituted quinones. In sometimes in nature you may also find compounds which are like your furanoquinones. Now quinones, especially your benzoquinones, are found in families such as Leguminosae, Asteraceae, Myrcinaceae, Comfreraceae or Araceae. Not only that, they also occur in some species of fungi, and these are very potent ones. So they have what are called as anti-inflammatory activity, but they have a ability to ward off the parasites. So they also show to certain extent anthelmintic properties, especially if you go to see quinones such as embelin. Now let's take an example here of drugs containing benzoquinones. In today's session, we will study two drugs containing benzoquinones, and that is Embellia ribes and Nigella sativa. We will first discuss Embellia ribes, that is your Embellia. Now Embellia is a plant very indigenous to us. It is called as false black pepper or wouding. So traditionally fruits of this plants have been boiled and given as a decoction to children, especially to ward off the worms or for its anthelmintic effect. Now this wouding is actually a fruit, or more correctly referred to as dried berries of the trees of Embellia ribes. Now Embellia ribes is a deciduous trees which grows somewhere down from Maharashtra to South India. Not only that, down to Sri Lanka, Malaysia, or even in parts of South China it occurs. Now this plant is also cultivated for wouding, but majority of its produce is also still taken from the wild sources. Now once the plant is cultivated, within 2 to 3 years it starts fruiting. Now a good time to collect the fruit is generally during the summers, and if you have to collect a very mature ripe fruit with the seeds, you can collect it in the early monsoon when the fruits are very dark. But if you want to use it for pharmaceutical purposes, mostly it is collected in May or summers when the fruits are reddish, or they have this type of consistency. If you wait till late monsoon, they will become blackish in color, and then they are difficult to manage because they have a good content of tannins. So, even the decoctions or the preparations containing them become very dark. So, what does this embellia contains? Embellia contains chiefly a compound, especially a benzoquinone called as embellin. So, this is like how the pure embellin looks like. It's a nice crystalline sticky flake. It's little oleaginous because of the long chain or the aliphatic long chain. So, it's oily, it's nicely flaky orange color. The interesting part is if you break the fruit, okay, just see here, if you break this fruit open, you see the inner endosperm exposed. The content of embellin is so high and it's located on the outer wall of the endosperm. So, the moment you open this fruit in your hand, you will see some orange powder stuck to it. This orange powder is nothing but the embellin. Now, apart from embellin, it also contains a dimer of embellin, which is your villanogin. So, this is nothing but a dimer. So, imagine your embellin twice. You call it as villanogin, and it is often thought to be a byproduct or the deterioration product of embellin. Now, in addition to that, embellin has a C11 chain. Suppose if you change it to a C13 chain, you get the third quinone compound, and that is your rapinone. So, your embellia ribes contain chiefly embellin. It contains your dimer of embellin, that's villanogin, and a little long chain, that is C13 substituted benzoquinone derivative, and that's your rapinone. Apart from it, it contains volatile oil. It also contains fixed oil, certain resinous substances, tannins, alkaloidal compounds, crystambin, phenolic acids like caffeic acid, vanillic acid, chlorogenic acid, cinnamic acid, and coumaric acid. And that is the reason when you tend to consume it or when you tend to eat it, it has a slightly sour odor as well as taste due to presence of acidous substances. Now, where do you use embellin? Embellin is known in Ayurveda and it has been used traditionally even in folklore medicine. Like I said, the decoction of the fruits is given to eliminate the intestinal worms as well as the parasites. Not only that, consuming this water or the decoction of embellin has been reported or known to give you relief from abdominal issues such as indigestion, constipation, flatulence, or even abdominal pain. Now, with little modern day investigation, the fruit extracts are known to cure tumors of certain types, help in dealing with ascites, which is a water accumulation, bronchitis, jaundice, and even certain mental disorders. Now, if you see embellin, embellin is one of our anti-fertility agent. So, it is used in spermicidal creams. It is even recommended in Ayurvedic formulation called as Pipliyadi Vati. Now, this formulation is actually a tablet or a oral contraceptive tablet. Now, this contains embellia ribes as one of its ingredient. So, yes, it has anti-fertility effects, and that is something we need to be cautious when you are using it for other therapeutic purposes. The decoction of these fruits, apart from the above mentioned, also is useful in treatment of fevers, for disease of chest, respiratory disorders as well as skin disorders. The infusion of roots of embellia ribes have been prescribed traditionally for treatment of cough and diarrhea. Now we move on to the next plant, is something which is cultivated in India on a large scale now because of its increase in the usage. Now this increase in usage has basically happened in the hair care industry, where Nigella seeds are also sold as onion seeds. So onion seed oil is chiefly your Nigella seed oil. That's the another common name, or also referred to as your kalonji oil. So this is obtained from the seeds of Nigella sativa. Some people even call it black cumin, but it has nothing to do with cumin. It's not a Umbelliferae family member. In fact, it is Ranunculaceae family member. Now, this is also plant which grows, which is harvested generally during the spring season, and what happens is within 90 to 120 days your crop is ready. This beautiful black seeds are located in the capsules of the plant. So this plant after harvesting is threshed to break the capsules, and the breaking of the capsule releases the seeds. The seeds are collected, all the chaff is blown, and then what you get is Nigella or the kalonji seeds. Now this kalonji seeds have an enhanced or increased therapeutic value because it contains a compound, especially a benzoquinone derivative called as thymoquinone. Now the seed majoritarily contains fixed oils, little proteins about 16 to 19%, carbohydrates which is almost as equal to oil, fibers and moisture. But the thymoquinone is the one which is responsible for its majority of the effects. So it's a, like I said, it's an oxygenated terpene derivative, but you call it as a benzoquinone. Now that is present in the volatile oil. So if you take the seeds, distill it and collect the essential oil from this, you will see the thymoquinone gets collected in the oil almost to the extent of 20 to 30%. Now apart from that, the other essential components of oil include your cravicol, parathymine, paraterpineol, longiflorine and transenethol. So these are the other ones, and thymoquinone is a major part of volatile oil which is also responsible for a mild what you call it as antioxidant as well as the therapeutic effects of the oil. So what are the therapeutic effects? So traditionally, especially in the Middle Eastern countries or Far East countries, it is used, or kalonji oil as well as the kalonji extracts have been used to treat headaches, coughs, abdominal pain, diarrhea, even asthma and rheumatism. Now the increase or the utility of kalonji has been due to its lipid lowering effect and insulin sensitizing effect, which have been proven clinically. Now not only that, it is also been used to address digestive disorders like a carminative, that includes your indigestion, bloating and even certain cases of diarrhea. The kalonji oil or black seed oil is like nowadays included in your hair care as onion seed oil. Synonymously it is put in, and it has a good potential to promote hair growth. So one way, internal consumption for lipid lowering and increasing insulin sensitivity, that is related to your glycemic or diabetic effects or treatment of diabetic effects. On the other side, the external application which increases the hair growth and enhances like the hair care properties, especially the hair thickness. This too have caused an increased market demand of this seed. Apart from that, kalonji is also part of numerous hepatoprotective formulations, and in animal models it has been proven to be effective against carbon tetrachloride induced liver fibrosis and cirrhosis. So these are two quinone examples. Let's move on to a anthraquinone example. Now anthraquinones, unlike your benzoquinones, have a anthracene moiety. Anthracene is a, what you call it as, you have a 3 benzene rings stuck to each other. Now previously, if you remember, we have studied a few anthraquinones. Now this anthraquinones include your senosides. Your carminic acid is something we will discuss today, and if you remember your aloes, you had your aloin. So we have already studied under the glycosides category your senosides and aloin, which are example of anthraquinone glycoside derivatives. Now anthraquinones mostly, like I said, are 9-10. So this is like 9-10 compounds. Anthraquinones, mostly the para substitution is preferred here because that is more, or that is considered to be more stable. Now because of biosynthesis, you see most of them have a hydroxy substitution. So mostly your quinones will have some or the other hydroxy substitution due to your ketone of acetyl CoA getting reduced, and sometimes even the hydroxyl being added. Now because of the hydroxyl being added, majority of the quinones also add a sugar moiety and are converted into glucosides. A good example of anthraquinone containing drugs is your rhubarb, senna, cascara, aloe. They are there in certain insects such as cochineal. They are there in certain fungi. They are also found in certain lichens. In today's session, let's discuss one beautiful insect containing anthraquinone derivative, and that's your cochineal. So cochineal is actually a pigment which is derived from the insect called as Dactylopius coccus. Now this Dactylopius coccus is a very tiny insect, as you can see here it's covered. It's a very tiny insect which kind of feeds on the sap of cactus, and it prefers the sap of cactus called as opuntia. So it is opuntia loving plant, loving insect, and it is found mostly in the American subcontinent, in the Peru, Mexico as well as the Canary Islands. So that's where the cultivation of this is also done. So actually the insects have been cultivated, harvested, so they have been picked up, the tiny larvae of this, and they have been transported to cactuses. Now once they are transported to cactuses, they kind of stick to those cactuses and start feeding on its sap. Now this insects undergo diversion. So the males are generally found to be a little tiny, whereas female grow to a little big size like 3 millimeters or so, and they acquire pigment. The pigment is a part of their defense system. So they acquire this pigment so that they can ward off the other predators, and the female insects, as they mature, the amount of pigment goes on increasing in them. So once that is done, now this is actually a sessile parasite, so they don't really move. So once they have been stuck or attached to the opuntia, they will grow and dwell in the very same place, even they lay their eggs there itself. Okay, so this insects, when their harvesting time is there or when the harvesting time is due, the leaves are brushed. So all this insect kind of fall off. So you will see the process. So this female insects contain about 17 to 24% of their body weight of the carminic acid, which is the reddish color dye. So mostly they are brushed off. Then after they are brushed off, they are all collected on a paper or on a plastic bags. They are dried in sun. So they are made crisp, and this crisp insect is then kind of ground. This pounding or grinding creates a very fine powder. This powder as such is used for dyeing of textiles, but for pharmaceutical and food application it needs extraction. So for textile applications they just take the ground powder. For food and pharmaceutical application, this powder is extracted with solvent. Now the pigment which is present here is carminic acid. So as you can see, it's an anthraquinone derivative and it's an anthraquinone C glucoside. So what happens is the sugar cannot be kicked out easily because it's a CC linkages, and that sugars renders it little polarity. So I can extract this pigment in water, ethanol, acetone. In some cases I can heat to get more of this pigments. Then it is filtered, wherein the insects stay back and the filtrate contains your pigments. This is further concentrated and you get a nice dye. Now in some cases what is done is this dye is further reacted with metals such as aluminium and converted into lakes. Lakes are the insoluble salts, so they get converted from dyes to pigments, and in some cases the pigments also are used. So if you see cochineal, cochineal is used as a natural food colorant. It is approved with an E number of E120. Carminic acid or carmine, you have a color index number 75470, which gives a nice red tone. And the good part of this red color is it's very stable to light and temperature. Otherwise, most of the natural colors are not, and that makes it a more ideal pharmaceutical or cosmetic grade color because of its color fastness, and in some cosmetics you need to use temperature. So, it is very conducive to use a stable pigment than to use a red color pigment such as anthocyanin, which will lead to deterioration. Not only that, it shows a pH dependent color change. It is said that the carminic acid is more reddish towards a little acidic pH, and then the color changes to little purple as it goes to a neutral to near alkaline pH. Now, you can make different lakes. Mostly aluminum lakes are used. In some cases even calcium lakes are prepared, and apart from this, your carminic acid is also used to stain bacteria. So, it is used in bacteriological stains. So, these are few examples of quinones. What we did are two examples of benzoquinones, that is your ambelin and thymoquinone, and one example of anthraquinone compound, which was your carminic acid. But do not forget, we already have done two more additional anthraquinone containing drugs, and those are your senna and aloes. They also belong to the anthraquinone class of compounds. So, here are few more references if you wish to know more about this set of compounds, and thank you everyone for your patient listening.